Okay, so well, the question was, how do we know the equation for
Monte Carlo integration.
for Monte Carlo integration? Well, I mean, you need to have an equation to integrate. So at least that will be, that's got to be provided wherever you are, right?
Yeah, so so we proceed only from there, right? So we already know like the equations, then we just basically.
Yeah, somebody has to tell you we want the integral or an approximation of the integral of this equation, right?
Uh-huh.
And so that equation becomes your h of x.
I see. Okay.
Okay. And or whatever function it is, and you would integrate accordingly. Okay. Are there any other questions? I don't know if that answers your question, but I hope in that the equation, if I say we want the integral of something, that function needs to be provided, right? If we want the integral of a function, you need to know what that function is. And so in the homework, I said, let's find the integral of this function, this funny looking thing, and that's fine. So, okay. All right. Then let's go on to our next topic, which is I'm having trouble finding my cursor here. Okay, here we are. It's called importance sampling. Okay, and again, I think a better name might be weighted Monte Carlo estimation. Okay, and so for for Monte Carlo estimation, we want to estimate, what is the quantity that we want to estimate? We want to estimate the expected value of some function h of x if it's applied to a random variable defined by PDF f. Okay? So this is the expected value of a function h of x if it is applied to a random variable defined by PDF f. Okay? And so, for example, if h of x is the function x squared and f is the normal density, then the expected value of h applied to the normal density would be the expected value of a chi-squared distribution with 1 degree of freedom. Okay, and we said this is equal to the integral of h of x times f of x dx over the domain D. Okay, and what are the steps for getting an estimate? The process is what? What's the first thing we do? Yeah, generate random values from where? Yeah, we generate random values from f of x. Okay, then what do? We apply h to the random values, and then we get what? Take the sample mean. Okay, so that process is, I'm hoping by this point, straightforward and it makes sense. And it might involve a little bit of mathematical manipulation to get whatever, whatever function it is that you're going for, you got to get it into the form of h of x, some function, multiplied by a PDF f, okay? So, it maybe requires some manipulation to get things in the form h of x, which is any function, times f of x, which needs to be a PDF, okay? And the requirements to be a PDF is that it has to integrate to 1 and must always be positive, right? Okay, and there's a major assumption, and the assumption is step 1, where we generate random values from f of x, is easy, okay? Assumption is step 1, generating random values from f of x is easy. And if it's not, then we're going to have some issues, okay? And so today's lecture, importance sampling, covers the case when f of x, the function that we're trying to generate values from, is not easy, okay? So what do? Okay, so what do we do if we can't generate values from f of x easily? Okay, or we do not want to use f of x, for some other reason. Okay, well, the answer is it's okay. Just use some other function, all right? If f of x is some crazy distribution, just say, all right, I'm going to generate values from g of x, okay? And that's fine, okay? But we just have to take that into account. So the answer is, that's fine, okay? And we will generate values, we'll generate random values from another function. Okay, g of x, okay? So that's fine, we'll generate random values from another function, okay? And again, g of x has to be a PDF, okay? So g of x, so the requirements are that g of x is a PDF. So I guess it's not just any arbitrary function, but g of x is a probability distribution. Okay, and the support of f of x must be fully contained within the support of g of x. Or, the domain of f of x must be, a subset or fully contained. In the support of g of x. Right. So if if the function f of x is negative infinity to positive infinity, then g of x needs to go from negative infinity to positive infinity, okay? If f of x goes from 0 to 100, then g of x has to at least go from 0 to 100. It can be bigger than that, but it has to at least contain whatever f of x has, okay? So the support of f of x must be inside g of x, okay? And then we will call g of x the candidate or trial distribution. Okay, and so what do we do? All right, so keep in mind what we want. We want the expected value of h of x if x is a random variable defined by f. Okay, that's what we want. We want the expected value of h of x if x is defined by the random variable f, and this is going to be equal to h of x times the PDF f of x dx. Okay. So instead, though, I'm going to just throw in some g terms, okay? I'm going to divide by g of x and multiply by g of x, okay? And so this, because I'm multiplying by g of x and dividing by g of x, I'm not really affecting anything, okay? So remember, this is in the form of arbitrary function times a PDF, okay? We're in the form arbitrary function times a PDF, okay? Can I factor this into an arbitrary function? Yes, okay? So this becomes our arbitrary function times a PDF, okay? So we're still in the form of just some arbitrary function times a PDF, okay? So then this becomes what? This becomes the expected value of the arbitrary function, which is not h of x, but what's my arbitrary function? It's h of x times f of x divided by g of x. If x is defined by the function, what? G. Okay, so here's the expected value of function h if applied to a random variable defined by f, okay? And this is equals the expected value of h of x, f of x over g of x applied to a random variable defined by the function g. Is that okay? So now we've avoided the problem. We couldn't generate values from f of x, so we're going to generate values from g of x instead, okay? So we say f of x, for whatever reason, this is a PDF that I don't want to generate values from. Fine. What are you going to generate values from? We're going to generate values from g of x. Okay, but what we want is the estimate of the value h over the random variable defined by f, okay? So in order to keep things equal, we just include this term, f of x over g of x, and so these two things are equal. I mean, does the math make sense here? Okay, and so now the method, so to estimate this without generating values from f of x. Okay, what is our first step going to be? Generate random values from what? Exactly, random values. We're going to generate random values from g of x, and then we will apply the function. What's the function that we're going to apply? H of x times f of x divided by g of x to all the values. Okay, and then what do I do? It's exactly what you think we should do, which is take the sample mean, right? Okay, and this works. Yeah. And take the sample mean. Okay. Does that feel crazy that this would work? It feels a little crazy, but it's okay, all right? Because, I mean, mathematically it makes sense that these are equal, okay? But, you know, the process feels weird. We're like, what? We're not even generating values from f. We're generating values from something different, g, okay? All right, so just kind of intuitively, this is, I don't know, this, you know, it makes sense in my brain. Of course, maybe intuitively, all right, let's just say, all right, so here, let's say this is my function f of x, okay? So this will be f of x, all right? And let's say we just have, let's say, just to keep it simple, let's just say h of x is equal to, like 1, okay? We're just gonna take, or it doesn't even matter, okay? Whatever h of x is, it doesn't matter. We want to figure out what this should be. All right, so this is f of x, and then let's look at, and let's say we can't generate values from there, but we're going to generate values from here, okay? Pretend this doesn't go under the, oh no, that's not what I wanted. Okay, we'll just leave it. All right, so this is what we have, all right? So, let's take a look at, let's say, let's look at this value, x super 1, okay? So, if we look at the PDF of f of x versus g of x, okay? If we look at the value at x1, okay? Let's just say, all right? So if we generated values, I would say, if we were able to generate values from f of x directly, you know, we would generate the value x1 about twice as often as we would when we sample from g of x. Okay, do we see that? So because Oh, I'm sorry. Not twice as often, half as often. Okay, that's my bad. Okay, because f of x, the line for f of x is half the height of the line of g of x. Okay, so we would generate. So if we were able to generate from f of x directly, we would generate these values of x1 about half as often as we are under g of x. So by using g of x instead of f of x, I'm getting twice as many x1s as I should. Okay? So what we do is to calculate the expected value under f rather than g, I weight those values by the ratio f divided by g. Okay? So if we're able to generate, we would get x1 about half as often as we would when we sample from g of x. Okay? So basically, so my sample from g of x, contains twice as many x1s as it should. Okay, so to calculate the expected value of h of x over f, we weight the quantity h of x by basically 1/2 the ratio of f of x divided by g of x. Okay, because we're saying we got too many of these things. So these things are going to be made to be worth only half as much. Yeah. Is that all right? Okay, and then on the other hand, over here, like if I come over here, and then let's say call this x2, we basically have the reverse situation. Under x2, okay, so at x2, our g of x does not produce as many x2 values as f would. Okay? It only produces like, I don't know, 2/3 as much. Okay? And so whenever we get one of these values, we're going to say, oh man, these ones are extra important, so we're going to weight them more heavily. So we give each thing an importance weight. Okay, we say, under the real distribution f, I should be getting this much, and I'm only getting this much. So each one that I have is, 1.5 times as important, or whatever it is. Okay, and over here I'm getting too many, and I only needed this much. So the ones that I have, they are less important, and we weight them accordingly. Okay, so does not produce as many x2 values as f of x would. So, when we have a value x at x2, we weight them more importantly. Okay, meaning f of x over g of x is greater than 1. Okay. And so by including this, what we call an importance weight, which is just the ratio between the two PDFs, we're able to compensate for the fact that we're drawing from g of x instead of f of x. Okay. All right. Are there, I don't, does that kind of, I don't know, make a little bit more sense as to why this is working? Yes, question.
So for g of x,
Uh-huh.
how did you decide that it should be like a normal?
But it was just arbitrary.
Okay.
Okay? It doesn't even, so theoretically, you could pick any PDF g of x as long as the support of g of x fully contains the support of f of x. Okay? So whether, you know, if f of x has this shape, you know, I could have done a uniform one, okay? I could have done this normal looking one. I could have done any shape g of x. Anything would have been fine, okay? And theoretically, in the long run, it works out, okay? But, you know, maybe in the short run, ideally, it works better if f of x and g of x are, you know, more closely aligned. Yes, question?
If we can find out the value of f of x to find like the ratio to g of x, why would we ever even assign a value? Why don't we just use f of x?
Yeah, so yeah, this means that we need the PDF of f of x, okay? And we need the PDF of g of x, okay? However, just because you have the PDF doesn't mean it's easy to draw samples from f, okay? So case in point was we have the PDF of the normal distribution, but it's actually not that easy to get random values from the normal distribution via like inverse CDF, because the inverse CDF doesn't exist but now we have this computational approximation that works really well, right? So just because you have the PDF doesn't mean generating random values from it is easy, okay? Maybe it's doable, maybe you can integrate it, maybe you can invert it, but it might be quite difficult, okay? So, but yeah, that's a totally legitimate question of if I've got f of x, you know, why not just generate from f of x, okay? And the answer is it's not always easy to generate from f of x, even if you know exactly what it is. Okay, so, you know, we must know f of x and g of x, okay? And but it may not always be easy to generate values from f of x, okay? And that's fine. We generate from g of x, which is easier. Okay, theoretically, any PDF g of x that fully contains the support of f of x will work, okay? But on a practical level, the method works best if f of x and g of x have similar shapes. Okay, so let's revisit an example. Okay, so let's say our example is we want the expected value of the folded normal distribution. Okay, which is this thing, right? So it goes from 0 to infinity, right? And so this, it's basically the positive half of the normal PDF but because it has to integrate to 1, it's going to be twice as tall, okay? Okay, so f of x is equal to 2 times the normal PDF for x on the interval 0 to infinity. So we have 2 times 1 over root 2 pi e to the negative x squared over 2, okay? And we will pretend that it is hard for us to generate values from f of x directly, okay? Okay, so I mean, we know that we can generate values from the normal PDF, and all we have to do is throw away all the negative values, or we can just take the absolute value of all the things, and we would get values from the folded normal, okay? But we're going to pretend that it's hard to do this. Okay, so, and let's say we want to get the expected value of this function, the expected value of this distribution. Okay, so basically we want the expected value of x over f of x, over the distribution defined by f, right? So here, we want this. And so this is going to be what? We want to get this in the form d of h of x times f of x dx, okay? So what is our h of x? It's just x, right? Because that's what's inside the parentheses, okay? And then our f of x is 2 times 1 over root 2 pi e to the negative x squared over 2. Okay, so we pretend that it's hard. Okay, so let's say, all right, so we don't want to, for whatever reason, we don't want to generate values from f of x. So, okay, so we won't generate values from f of x. All right, so what do you think is a good distribution g of x? Okay, we will generate from another distribution g of x, okay, which has to be defined on the same interval, defined on at least 0 to infinity, right? Okay, so maybe a candidate g of x can be just the exponential distribution. Let's use a exponential distribution with lambda equal to 2. Okay, so g of x is, lambda e to the negative lambda x. So it'll be 2e to the negative 2x. Right. So we're going to generate values from g of x. Okay. And so now what? So to estimate the expected value of x over f, we're going to get, which is this, x times f of x dx. We're going to do the expected value of x times f of x over g of x times g of x dx. This will be our function, so this will be the expected value of x times f of x over g of x over the distribution g. To estimate this, we can estimate this. Okay, and so our process would be generate values from g of x. This will be exponential with lambda equal to 2. And then step 2 will be calculate x times f of x over g of x, okay? Which is going to be for all random values. Okay, so this is going to be equal to x times 2 over 1 over root 2 pi e to the negative x squared over 2. And this is going to be divided by 2 e to the negative 2x. So here I get x times 1 over root 2 pi, and then combining these, I get e to the negative x squared over 2 plus 2x. Okay. Where x comes from the exponential with lambda equal to 2. All right, and then 3 will be just take the sample mean. Okay, so let's try this out. Is it all right? All right, so we're going to generate x from where? We're going to use random exponential. I'll ask for 1,000,000 of these values where rate is equal to 2. Okay. And then f will be the function 1 divided by square root of 2 times pi times e to the negative x squared over 2, okay? And g is going to be a function, function of x, and it will return negative 2 times e to the, I'm sorry, not negative 2, lambda times e to the negative lambda times x. Yeah. Is that okay? All right, and then so what do? We're gonna generate this, and then our h, I mean, this seems unnecessary, but it's just x, right? our h of x is just x. Okay, so what we're going to do is we're going to generate x, and then I guess I'll just call this k. K is going to be the product of h of x times f of x divided by g of x. And then I'm going to take the mean of k. So x comes to the random exponential. I'll calculate f for everything. I'll calculate g for everything. And I'll calculate h for everything. And then I do h of x times f of x divided by g of x. That gives me k. And then I take the mean and I get 0.3987. Okay, so this is the estimate using importance sampling. Okay, let's just compare that to the direct Monte Carlo method. Which is, I'll call this z. Z will be our norm. I'm going to ask for 1,000,000 of these things, 1,000,000 random normals. And then, and if it's the folded normal, I can just take the absolute values of the z, and then we can just take the mean of the absolute values of z. Okay? Okay. Did I mess something up? Oh, see, nobody caught me. Okay, f of x is 2 times the square root. 2 divided by the square root of 2 over 2 pi, right? Okay. So this makes the difference, right? Okay, so we have f of x, f, g, and h. Okay, I run this, and I get, and this is my estimate using importance sampling, and then the estimate using the direct Monte Carlo method, which is random normal, and then taking the absolute value basically folds the distribution. Okay, and we get something very, very similar, all right? Very, very similar. So one is the importance sampling, and the other being the direct method. They both work, okay? So even though you are not using the true distribution to generate your random values, you still get accurate estimates. Okay, we'll end there.